Okay, thank you for joining the webinar today. My name is Greg Johnston. I'm a product manager, and I've been with Sensors and Software for 33 years. Sensors and Software has been a part of radio detection for 5 years, since 2020. So today we are going to discuss mapping utilities with ground penetrating radar, or GPR for short. Okay, so the agenda is going to be where I'm going to talk about marking the position of utilities, and then we'll talk about using an onboard GNSS for mapping utilities. And then the bulk of the presentation is going to be talking about the details of data collection. So 3 different methods for collecting data and mapping utilities. And then we'll have a short section on other GPR applications where GNSS is especially suited. And then, as I mentioned, we'll have a Q&A session at the end. So no matter what utility locating technology you're using, an EM precision locator or a GPR, marking the position of detected utilities is critical. So one method of marking the position is paint on the ground. And this is certainly the solution for many utility locators. However, some customers want a more advanced, more permanent positioning solution, and that is a digital map of the utilities. So here's one way to get there from paint on the ground. You mark the utilities by putting your paint on the ground. You call a professional surveyor to come in with his high accuracy GNSS. He or she marks that, and that information goes into a digital format that can then go into mapping software. So the issue with this workflow is that one is labor intensive, it's more time consuming, and it does require some of the steps in here require advanced training. Specifically, the surveyor is usually a highly skilled individual, and therefore a very expensive individual as well to come out to the site. But ultimately, your goal is you want to create that digital map. So the better way, we think, is to map while you're locating. And do that by having an onboard survey grade GNSS. And some of you are going to be familiar with the RD8200SG, which came out, I guess, a couple of years ago now, where there's an onboard GNSS that allows locating data to be captured digitally, and then you can take it into mapping software, like shown on the right here. So it's not a big surprise that I'm going to make an announcement that we actually made last month, which was that Sensors and Software now offers an optional GNSS, and specifically we're using the one called Geode, the Geode manufactured by Juniper Systems from the United States. And the Geode has an accuracy in its native format, in its base format, of about 0.3 meters, which is a step up from a lot of GNSS systems. And 0.3 is you're getting about the size of a shovel or certainly an excavator. So you're getting in the range of the accuracy required for locating utilities. Further, the Geode GNSS can be upgraded with RTK capability, real-time kinematic, and that can increase the accuracy to centimeter level. We can get down to 0.01 meters. So to do that, the Geode needs to have the RTK upgrade. So there is an additional software upgrade that can be done remotely, actually, in order to give it the RTK capability. Now, RTK accuracy also requires a cellular or satellite-based RTK correction service. So this image shows the concept of how a cellular-based correction service operates. That is by using the Geode Connect app on a cell phone. So the Geode Connect app along with a base station with a known position, and all the satellites that you have available are going to correct the position down to that 0.01 meter accuracy. Now, I want to point out that the RTK correction service is typically a subscription service, and that's something the user must subscribe to and pay for. Although in some places they do provide a free version of this service. I know there's some states in the United States, and there's probably some countries around the world where you can get this service. It's also called N-Trip. So you look for an N-Trip service that's free of charge and see if you can do that. Otherwise, I just want it understood that even when you do have the Geode with RTK capability, there is an additional cost typically to get the correction service. So the Geode is compatible with all Sensors and Software GPR systems. Pictures of them shown here. So we got the LMX systems, the LMX 200, LMX 150 FINDAR, but also Noggin, and there's a few pictures of Noggin shown here, Pulse Echo and SPIDAR systems. And those are shown here in different configurations. So we have our Smart Tow, where the GNSS is actually in the backpack that's being carried by the operator. We see the GNSS on smart carts, either the Noggin smart cart or the Pulse Echo smart cart. We have the Smart Chariot, where you can see the GNSS. There's a little mount right on there, so you get the positioning as you're driving. And also in the Smart Sled. Now it's actually under the cover in the Smart Sled. This is not a metal cover, so we're good with the signal. And that positions you as you're towing the system around with the Smart Sled. So the point is, we've got this capability is now available for all Sensors and Software GPR systems. Now, the systems I'm going to talk about mostly today are LMX systems, which are designed around utility locating. But we do have a bundled system, and so we have the LMX 200 in a bundled system, and the LMX 150 in a bundled system, and that includes the base version of the Geode. And so if you're interested, the part numbers are right here, and so it's our standard part number just with a -SG on the end of it. Now, we have some value adds to the Geode that we're providing with the GPR systems. We're not just reselling the Geode. There are some things that we've done with the Geode that add some value to this process. So the Geode is pre-programmed to work with Sensors and Software GPR systems. If you just buy a Geode and plug it in to our system, they're not going to talk. The data logger is not going to talk to the Geode. But there's some programming that needs to be done, and that's all looked after when you get the Geode from us. The second thing is, because GPR is typically a moving platform, you are collecting data on carts or towing it or dragging it. We need more frequent updates of the position. So the native version of the Geode provides 1 Hertz or 1 position per second. But in 1 second, you could probably easily push a meter, meter and a half, 5, 8 feet. And so we need more position so that you have a smooth path. So we also offer the Geode with a 10 Hertz upgrade. So the 10 Hertz means we're getting 10 positions a second, which means you're probably going to get into the sub-foot. We're getting a position every few inches. So that in the end, we get a smooth path. And that's very important for a moving platform. The last thing is that the cable that we're providing with the Geode is a special cable that does 2 things. It powers the Geode, which means that we can use the battery on the GPR to power the Geode. And that way you don't have to worry about making sure that the battery on the Geode is charged up. You may have had that experience of going out in the field and finding, okay, my GPR is ready to go, but the GPS battery, I forgot to charge it. And so now I'm stuck. I got to go back to the office, or I've got to wait for it to charge. That's not going to happen in this case. We can always, the Geode will always be powered by the battery on the GPR system. The other thing the cable does is cables can be a source of noise in GPR data. And so we've done some changes. We've added some things to that cable to reduce the signal interference with the GPR data. And so that's, we've minimized that so you don't see problems with noise with the data. All right, so now, along with the RD8200SG, the EM precision locator I mentioned earlier, all Sensors and Software GPR systems are now part of the Map It Your Way products from Radio Detection. So you can see the Map It Your Way emblem that we have there, along with the concept of what we're doing. So as you're collecting the data, you're also collecting the data digitally so that you can go straight into mapping utilities. So let's get into the details of what this actually means. So just like the RD8200SG, the deliverable is a geo-referenced breadcrumb path of utilities. That's what we want. We want to map them. We want to find them at discrete locations, a bunch of dots that follows the path of the utility. And that's shown here in this type of view called SplitView. And I'll talk about, you're going to see a lot of SplitView in this presentation. So on the left-hand side, we see a cross-section of the GPR data and a hyperbola. Hyperbola is the standard response that you're going to get from an object in the ground. On the right-hand side is the path that we've followed. So you can see this, in this case, it was a zigzagging path, and we've added interpretations, in this case, a pink dot to the top of the hyperbola, because that's the actual location of the object. And then when we look at that series of dots, we see that it forms a straight line. And so that gives you a strong indication that this object in the ground is linear and therefore is more than likely a man-made object and is more than likely a utility. So that's how we narrow things down. So we're going to talk about SplitView and how we use SplitView to map. So to create a map, it starts with using the high accuracy positioning of the Geode GNSS to your advantage. So that advantage is locating by simply scanning the area of interest by collecting what we call a pseudo-grid. This is shown in this video. So note that it's sped up to save time while showing the concept. So basically, we're covering the area of interest by walking back and forth or zigzagging across the area. You can see we've superimposed the path so you can see the coverage that we're doing. Now, some pseudo-grids are going to be tight line spacing like this, especially if you want to produce depth slices, which I'm going to talk about in a while. The other type of, the other way of collecting a pseudo-grid is you might want to do a coarser line spacing. So if the utility is on its own, or there's very little congestion, you may be able to get away with just locating the utility every 10 feet or every 20 feet and follow it very quickly down the street or down the throughway, that sort of thing. And so we're going to see that pseudo-grids vary in their line spacing for sure. The other element in mapping involves adding what we call field interps to the hyperbolas in the data. We know that the utilities are going to form hyperbolas in the data, and we need to mark those, and that's shown here. So you select the color of the dot. In this case, they're picking a pink dot and a blue dot. And so you pick the color of the dot and you touch the screen at the top of the hyperbola where the utility is located. If you make a mistake, you touch the dot again, delete it, and add it to the correct location, or don't add it at all. So in this case, we see two hyperbolas on the same line. So they must be two separate utilities. Therefore, we add interpretations with different colors, pink and blue in this example, to keep them sorted out when we view them in a map view. When you combine adding field interps to hyperbolas and the high accuracy GNSS that positions the GPR survey path and the field interps very accurately, you can map utilities while you collect the GPR data, as shown here. So in this case, we've got two utilities, a blue one and a pink one, that are actually crossing one another, so forming this X pattern but you can see by zigzagging back and forth over them, we can see the two hyperbolas, mark them, and produce this map image, this georeference map image that is accurate down to decimeters or centimeters. So once you've collected that data, your output files, there's multiple output files available, but the ones that are going to be particular interest for people who are mapping are the CAMZ or CAMZ files and the CSV files. So CSV files are just spreadsheet files. We've all seen those in Excel, that sort of thing. It has all the information in a spreadsheet format. So these are the file types that our most third-party mapping software use. And so these are the files come straight off of the GPR data logger, and they can go straight into mapping software. So let's have a look at some examples. So probably, I would dare say, the most popular mapping software in the world is Google Earth. And so you can take your CAMZ file and open that in Google Earth. So straight off the GPR into Google Earth, and we would get an output like this. So we see the GPR survey path in green, and we see the field interps that are added, the blue dots and the pink dots shown in color there. And we can zoom in and look very closely. We've made the dots very large so that they're easy to see, but the actual location is right in the center of those dots. Okay, other mapping software, another package that you might be familiar with is called PointMan. And PointMan was developed by ProStar. And if you've been keeping up with our company, you may have recently heard that Radio Detection has announced that it has signed a strategic collaboration with ProStar and is going to be using their PointMan software a lot more in the coming period of time. So here is a CAMZ file opened in PointMan. So same sort of thing that you see in Google Earth. We see the path. In this case, the path that was followed during the survey is a black line. And we see the interpretations, the field interpretations depicted as points in here. Another mapping software tool that many radio detection customers use is called Subsurface Maps. And here's a CAMZ file opened in that software. And again, we're literally taking right out of the field, open it in this software, everything's in place. It's a 30-second process at the longest. And arguably the most popular mapping software is GIS software. And so that's software like ArcGIS or QGIS. So in this example, I'm showing QGIS, and it typically reads the CSV file or the spreadsheet file that comes out of the GPR system. And so that's what we've done here. And I put in a different background. All the other ones show sort of satellite images, but this one shows a sort of a cartoony depiction of the streets and parks and buildings around the area. So that's one of the powers of GIS software. So the point is, we're taking our mapped data out of the field into mapping software very quickly. No processing required except what you've done out in the field. So let's look at how we create the CAMZ and the CSV files with the coordinates of utilities in more detail. So there's three simple methodologies to create utility maps with an LMX GPR. And so I'm going to be talking about the LMX specifically because it has the SplitView screen available on it, and I'm going to be using SplitView a lot. So we're talking about mapping with an LMX GPR and a high accuracy GNSS. And so we can do three things. We can add field interps in real time. We can add field interps in post-survey. And we can add MapView interps to depth slices. And so the third one is certainly different than the first two, but I'll get to that one in a few minutes. So let's talk about the first one. Again, we start with data collection in a pseudo-grid. As I mentioned, pseudo-grids can be a tight line spacing like this one is showing, or if you're following a utility in a simple setting, you could have a much coarser line spacing, as I'll show in an example a bit later. So I just want to point out the implications of zigzag data collection with GPR. When you cross two or more utilities in one line, each zag is the mirror image of each zig. So that's what this example shows. We have crossed two utilities. One is shown in blue and one is shown in pink. And so as we zigzag over it, the pattern is going to change to mirror image. So as we cross in one direction, we're going to cross the pink one, then the blue one. And then when we come back, we're going to cross the blue and then the pink, and so on. So you get this pink, blue, blue, pink, pink, blue, blue, pink, pink pattern when you're crossing two utilities. And this is important to remember when you're interpreting and adding field interps to the data. All right, so method one is adding field interps in real time. So this video is sped up to save time. It shows someone collecting data across two utilities that cross each other in the X pattern. And so the deeper hyperbola is marked with a pink dot, and the shallower hyperbola is marked with a blue dot. And each time the operator sees both hyperbolas in the cross section on the left-hand side of the screen, they stop and they add the colored field interps. So you see that process going on. It's sped up, but I think you can follow what's going on. As soon as you see the two hyperbolas, you know the deeper one you're going to put in one color, and the shallower one you're going to put in another color. Now, if you watch closely, the user's making all kinds of mistakes, accidentally putting the pink dot on the blue one, but they're correcting it. Once they realize that the utility is not going in a straight direction, which it typically would be, they're correcting. They're deleting the dot and they're changing it to the other color. So in the end, we have this X pattern of the blue dots and the pink dots. And again, with a high accuracy GNSS, it's all geo-referenced. And so we can go straight from here into mapping software. So method two is adding field interps in a post-survey step. And I think this method works better than adding the field interps in real time. You collect the data, you spend your time collecting the data, and then spend a few minutes adding field interps after you've collected the pseudo-grid. So this is the split view screen on the LMX GPR systems. You've seen this screen a few times now during this presentation, but let me explain in detail so we all understand what we're looking at. On the left is the cross-section view of the GPR data. We're looking at about 10 meters or about 30 feet of data horizontally and about 3 meters or about 9 feet of data vertically. You can see the nice hyperbola from our target that we think is the utility. That's the one we're chasing, and we'll follow that in just a couple minutes. On the right side of the screen is the bird's eye view or the map view of the survey area. You can see that the survey was a pseudo grid with the operator zigzagging back and forth over the target. The accuracy of the pseudo grid path is dependent on the accuracy of the GNSS used with the GPR system. The better the accuracy, the more accurate that path is. Now, one of the critical elements of the map view on the right is the orange line superimposed on the GNSS path. The orange line shows the length of the cross section on the left. In this case, 10 meters of length. So when you're looking at the split view screen, always note the orange line because that indicates the part of the cross section being shown on the left. We are not looking at the whole line, which is probably close to 100 meters long. We're only looking at 10 meters at a time. And that is shown, that amount of data is shown by the orange line. So you can move the orange line to a different part of the cross section. And this allows you to quickly line up hyperbolas from the same utility. So the start of the GPR line, position 0, starts at the beginning of the orange line. So note that the hyperbola is about 2 meters in at the start of the line. So let's add field interps to the hyperbola, move the orange line, and then add more field interps and see if we can follow this utility and confirm that it is a utility and also map it. So we put a pink dot on the hyperbola, we move over to the next adjacent spot. We see another hyperbola, we put a pink dot on it. We see in the map that they're lining up in a straight line. That gives us a strong indication that this is a utility that's moving across the area. And so inside of a minute here, in our post-survey step, we have confirmed that this series of hyperbolas line up in a nice straight line and give us a strong indication that they are a utility. And we've got a very accurate indication of the depth as well. So that's the method. And so we're going to do this in different scenarios here. So this is as simple as it gets, following one hyperbola across an area. Let's move on to another situation. So here's an example of adding field interps to 2 utilities on the split view screen. So the orange line in this case is 10 meters long, and we've got a long stretch of data, and then it goes around the curve and starts into the next pass around. So in this case, we need to remember, because there's 2 or more utilities, we need to remember that each zag will show the utilities in a mirror image of each zig. So the good news, as you will see, is that when we make a mistake and give a hyperbola the wrong colored dot, which is very easy to do, it becomes very obvious very quickly because the colored dots don't line up properly. So we can quickly delete the mistake and pick the right hyperbola that makes the dots line up properly. So let's follow that. So the first thing we do is we put a yellow interpretation on the one hyperbola, we move. Now we know that it's going to switch back and forth. It's going to be on the right-hand side on one image, and it's going to be the left-hand side on the other image. But if we don't follow that, if we're not paying close attention, you just put it on one of the hyperbolas, and you'll see whether it lines up or not. So in this case, I think we're about to make a mistake. We're not sure which one it is. We click that one. No, that's not the right one. So we delete it, and we put it on the right hyperbola. And so now the next step is a lot easier because we've already marked one hyperbola. So we switch to a red color, and now we're just putting a red dot on the top of the second hyperbola. So we shouldn't make any mistakes because there's only one hyperbola to pick at this point. So we work our way through the data, and the orange line gives us a good indication of what screen to expect to see the hyperbola on. We should expect to see it adjacent to the previous dot that you put on the screen. So in the end, again, inside of a minute, we have mapped these 2 utilities. And so we can output this as a CSV file or a KMZ file, bring it into our mapping software, and we're good to go. All right, let's up the ante. Let's go to 4 utilities. And this is, again, an LMX 200 cross-section, but it's a much coarser pseudo-grid. You can see in the lines that each zig and zag are about 5 or 10 meters apart. So the line is also 20 meters long, you can see in there. And there's 4 deep hyperbolas, and those are the ones we're chasing in this case. There are other hyperbolas, but in this case, the ones I'm particularly interested in are the deepest ones. And those are the targets that we're going to confirm are utilities and map their paths. Now, I have added some annotations to this video to help you follow along what's going on, but I will also provide a play-by-play. So we're going to start, we've got our 4 hyperbolas all in one line. And so we know there are 4 unique utilities, or at least 4 unique objects. So we're going to start by putting a different colored dot on each of the hyperbolas. So we changed the color to yellow. We put the first one, we put a yellow dot on. We changed it to red. The second one, we're putting a red dot on. The third one, a green dot. And then the one over there is a blue dot. So now we've got that established. So now let's start chasing the blue utility. We move over to the adjacent line. We move the orange line and we say, okay, the blue one, we think it's that one, and it lines up nicely. We go to the next zig or zag and we see the blue one is also the shallowest one. So we pick it out. That's one of the ways we're looking at it. It also has similar character each time. So there we are following the blue dot, another blue dot, back and forth. And you'll see that it varies in strength, but the character is definitely similar in every case. So we get to the far end, we put the last one in, we move back to the start. So we can start working on the next one. And the next one is the yellow one. So the yellow one is the one extreme, it's of the four, it's the one that's furthest away from the blue dot. So that's what we're looking for. We're looking for these 4 hyperbolas, and we're picking the one furthest away from the blue one now. Now you can see that some of these hyperbolas are really fading, and that happens with GPR. Those of you will know that sometimes they fade so much you don't even see them. But in this case, there was a patch where the response was much, much weaker. And we're going to see that with definitely the last 2 colors as well when we go to chase those. So we go back to the start and we figure out, okay, the next one we want to chase is the red dot. So the red dot is closest to, it's the hyperbola that's closest to the yellow. So we look for the yellow hyperbola, we find the closest hyperbola to the yellow one, and then we put that in red. And again, we're looking at our map and we're saying, these are all lining up nicely. We're looking at them, the character of them, and we're saying similar depth, similar character. Now in this case, it's getting dicey because we see a very, very faint red. Here we don't really see the red hyperbola, so we're not going to mark it. But we're going to move on. We're going to move on and say, okay, now the hyperbola is coming back. I see it very faintly, and I put it in there, and it lines up nicely. Now it's much stronger. I've got a lot more confidence picking that one. And now I'm at the end of the line, and I do see it. It's faint, but I can definitely see it. And this happens with GPR. This happens. You can cross a utility 10 times. If you see it 8 times, that's great data, right? There's going to be situations where, for whatever reason, high attenuation or whatever, you're not going to see that hyperbola. And so by marking on either side of it, again, if you see it 8 times out of 10, there's a lot of confidence that it's there. So in this case, we are gone back to the start, and now we're going to track the last one, which is the green one. And we know the green one's going to be between, green's going to be between the red and the blue. And so we're looking for that hyperbola, and it's going to be very close to the red is the other way to look for it as well. So in here, very, very faint. And if this was the only data we had, I probably would never pick that out as a utility. But the fact is, we've got multiple passes over top of the utility, and therefore that very, very faint hyperbola just in amongst the noise, I have way more confidence picking it as a real object, a real event in the GPR data. And so there we have it. Inside of 4 minutes or so, we've gone through all our data and we've mapped it out. In the end, we've mapped 4 utilities for 100 meters or more. So once we're done adding those field interps, again, we download the data so we have them in the KMZ or CSV files so we can use it with our mapping software. And so here's the resulting KMZ file plotted in Google Earth, showing the paths of the 4 utilities as well as the zigzag path of the GPR line. So notice that the area was not congested with utilities. We were able to zigzag at a very coarse line spacing, about 5 or 10 meters between these lines. And this allowed us to quickly locate and track 4 utilities for hundreds of meters in just a short period of time. All right, let's go to 5, and 5 utilities. So a much more complex situation, a lot more hyperbolas around that we're chasing, a lot more things that are going to trip us up a little bit, but let's see what we can do here. So in this example, we've collected the data, and in the end, we look back at it and we go, you know what, the best image of all five utilities is in the middle of the line. So let's start with our best data. And then we're going to work our way in one direction and then in the other direction to follow each utility. So right now, we are just adding 5 unique colors. So in this image, you can clearly see 5 hyperbolic responses, and we're giving each one its own color. Now we're going to start chasing, we're going to start tracking each individual color. The most unique hyperbola in here, which is probably maybe a non-metallic object, is the yellow one. You can see the yellow one has this kind of ringing effect to it, which may be that we're seeing the top and bottom of a non-metallic. And therefore, it's easy to scroll along and pick that hyperbola out every time. So we scroll, we look approximately where we expect it to be. There's a response that's very characteristic of every response we've seen before, and we put the yellow dot on top of it. We check our map and we go, you know what, everything's lining up beautifully. Everything, so there's a high degree of confidence that this is a utility. Now at this point, we are going to we're going to add the blue interpretation. So we know that the hyperbola that's close to the yellow hyperbola, it should be a blue one. Now we might put it on the wrong side, but when we do that, we quickly look at the map and we realize, okay, I put it on the wrong side. It's not the hyperbola on that side. It must be on the other side, like the mistake right there. Put it on the wrong side and realize that, oh no, the blue one is actually this very faint one on the side of the yellow one. So again, we're just following through the data. We're chasing the path. We're looking to where we expect to see it. And what this does is it gives you way more confidence in that very faint or very weak or very jagged looking hyperbola that you go, is this a utility or not? Well, if it lines up with everything else, then your confidence level goes way higher. Now, obviously, in some of these, the hyperbolas are very clear. There's no question about it. Other ones are way more iffy. But you go in there, you take a look, where should it be? Where do I expect to see this hyperbola? And in some cases, you can't pick it. But again, if you get it 8 out of 10 or 19 times out of 20, then you're doing well and you can certainly follow a path. So now we're moving on to the red hyperbola. The red hyperbola is the shallowest one. And so we move along and you're going to see it pop up. And when you zigzag, this one's close to the end of where we change direction. So the two of them tend to be close together. We see it there, and then on the next screen we see it close by. So you cross it, you go around the corner, and you cross it again. So that's all we're doing is we're putting in those series of red dots on either one. Now we're going in the other direction from our kind of our standard, which was in the middle, which was our best looking data. Now it gets a little bit more difficult in this part. You can see that that red hyperbola wasn't a very good one, neither is this one, but it fits. It fits with the pattern. All right, now I think we are moving to, we still got 2 more to do. You see, so this process is going to end up taking about 6 or 7 minutes. But it's a puzzle. What we're doing is we're putting the puzzle together at this point. You see the hyperbolas, it's just trying to match them. And so we've moved on to the green one. We know the green is going to be close to the yellow hyperbola, so that's where we're looking for it. Again, some of them aren't the best looking hyperbolas, but they are there and they align. And so this one, tough call. Now we're in an area where the green, now we're going to the other side and we're following the green one. That's a nice hyperbola, easy to pick. Another hyperbola, nice, easy pick on that one. And we're getting close to the end in the other direction. Now it's a bit faded, but it is there. And now we're into an area that's way more complicated and we're not spending the time picking the hyperbolas. Now we get over here and we realize, hey, wait a minute, there's a hyperbola that looks familiar. That's actually the yellow one. So now we've gone back and we're adding a stray yellow and to the two objects here that we didn't pick out earlier on. Because now we're picking up the pattern. We're seeing how all these hyperbolas fit together. So it turns out, oh yeah, there's the blue one there that we didn't mark earlier on the far end of the line. And one more in there, there's got to be a red one there somewhere. And there, so we pick that one as the red one, it lines up, confidence level goes up. All right, there's one more here. There's this deep object, which is purple. And this one is the trickier one because it really seems to interfere with yellow. It's deeper, but you can see it as in some of the sections here, you can see it as a unique hyperbola, slightly offset from the yellow. So we're moving along and there we do, we see it very faint. We put in a purple dot. And we're almost finished the process here. Now, we're not having a lot of luck in this direction, so we're coming to the other side of the purple dots. We're scrolling back through, and now we're looking for that deep purple dot, deeper than the yellow one. So anytime we see the yellow hyperbola, we're going to look for that purple one underneath of it and slightly off to the side. And there we go. We see it as a unique object. We go through the tough area that the GPR response just isn't that good in that area. And we get down to the far end and then things start to reappear again. Okay, and we're finished. So that took you through the entire process of interpreting 5 utilities and mapping them out. Again, with the GNSS, we have an accurate version of this. Okay, so here's the resulting KMZ file plotted in Google Earth showing the paths of 5 utilities. All right, let's move to the third method. The third method for mapping utilities with high accuracy GNSS is to use depth slices. So with a tight line spacing on your pseudo-grid, you can take the data into the Echo Project software and generate depth slices. Then you simply scroll up and down through the depth slices looking for linear responses that are likely utilities, like this example here. We see that at 0.9 meters below the surface, there's a red linear response, which is more than likely a utility. So depth slices may be new to some of you, but we have made this process very easy to do, especially the processing of it. So if you're interested in learning that, we have some short videos on our website, and I'd be happy to send you the link. You'll have my email address at the end of this. Send me an email. I'd be happy to send you the link so you can learn more about collecting data and then generating depth slices. And so here is depth slicing down, and here's the process of adding what we call MapView Interps. So MapView Interps are things we interpret in the MapView. So linear objects we interpret in the MapView. So you can see that we're slicing down and we got 2 different utilities. And there's actually a third one. There's a third one there that we just marked. And in the end, now it's going through the process again. Slicing down, 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 lots of red responses, but nothing really organized. And then we get down to this level, we see a linear feature. So we mark it, we draw an interpretation on top of it. We slice down deeper, we see another one, and we draw an interpretation on that one as well. And then we go back up and we draw a third one. So this information is all retained. Now we take that information, which is, again, all digital, all geo-referenced, and we can save it as a CSV file. and we bring it out into CSV is read by our GIS software pretty easily. And so here it is plotted in QGIS, the 3 utilities shown. Okay, I do want to warn you of something, a word of warning. I'm a big fan of depth slices. I'm a big fan of slice view lines that processes them into depth slices. But I want you to be aware that remember that depth slices are based on the amplitude or the strength of the reflection. The stronger the reflector, the more prominent it's going to be in a depth slice. So the hyperbolas that you typically see in a depth slice are strong hyperbolas. So weak hyperbolas, like the ones I'm showing here, like this is from that example earlier where we had those very weak hyperbolas, we can see them. We clearly see them with our eyes. But if we generated a depth slice out of this, they're probably not going to show up very well, if at all. They're probably going to be invisible. So because of this, this is why I'm a big fan of method 2. Method 2 is adding the field interps in a post-survey step. It only takes a few minutes, but in the end, you're counting on your eye to find all the hyperbolas, line them up, and now you've got them all geo-referenced and you can output them to your mapping software. So with that method, utilities that have weak hyperbolas can still be mapped. Or if you think about it, you could combine method 2 and 3 together. Find the obvious utilities with depth slices and the weaker utilities with field interps. That is a way of doing it. To finish off, I just want to show you some other GPR applications that can benefit from high accuracy GNSS. So we've talked a lot about utilities, and that was the main topic today, but there are certainly other applications for GPR, and there are applications where accurate GNSS can be a real benefit. So here's one of them. Here's a golf green drainage system. And look at the way the GPR data was collected. It could only be collected this way with a very accurate GNSS. So they basically spiraled out from the center into a larger and larger diameter all the way around. So this spiral image on there on the left side, and then the depth slices that are produced from that gives us an amazing image of the drainage in the Gulf green. Is one application. Now expanding that, we're taking the spiral that was collected and a pseudo-grid that was collected in the rest of the green, and we're taking all that data, combining it together and producing depth slices out of it. So now we can see the full drainage pattern in the Gulf green. And so as a combination of a spiral data collection and pseudo-grid data collection. So ends up with a spectacular image of what's in the subsurface. So the last slide I'm going to have today is high accuracy GPS or GNSS and in archaeology. And archaeology is actually probably the most fun use of GPR. Utilities are interesting, but not as interesting as finding tombs and buildings and things like that. So this is a data set, and you see it's slicing down. And so this is a Roman village or a Roman town in Italy. And this actually was released to the world press in the summer of 2021. And this was a survey done by one of our customers in Filuri Novi in Italy, just north of Rome. And I apologize to all Italians for butchering the name of that town. So it's an entire Roman city, and it was surveyed using a Sensors Software SPIDAR system. And the data really speaks for itself. You see buildings, you see streets, you can see the amphitheater in the lower section there, all by slicing down through the data. And how did they collect this? Well, they didn't collect it in small grids. They collected this by having a very accurate GNSS and towing around an array of GPR systems. And that's how they collected this, hectares of data. And then they process it into these depth slices, and you can see the layout of the entire town. And so another great application another terrific use of high accuracy GNSS. In the slide you're seeing right now, there is my email address. So when questions result from this, send me your questions even after the fact, and we'll make sure you get help.
There is another question, Greg, about using another GPS. So maybe you just want to comment on the ability. It says reach RS2, but in general, using other GPS with the LMX.
Yeah, there's other GPSs or GNSSs can be used with our products. The usual problem that people have is programming them so the two talk, so the GPS talks to our data logger. And the other thing that often people stumble with is the cable, because you need sometimes with some products, you need to get a serial cable that goes with it. I know in particular the MLID you can purchase. I'm not sure whether they send it out with every unit, but I know you can purchase a serial cable with that, and the serial cable will allow it to plug into our data logger. And if you are trying to get another GNSS working with our system, we do have a one-page help sheet. It's on our website. We want to get you up and going with this because it's a very nice way of collecting GPR data. Thank you very much for attending. Hope you got something out of it. And again, any questions, let us know. Thanks again. Bye-bye.